So good evening, guys. I hope you are able to hear me. Dinesh, Ivan, Andrew, everybody is able to hear me. If yes, make sure our video is on. We're going to start the class now.
Excuse
Yuvan,
me.
Yuvan, Rohit, everybody.
Sir,
Video
can you
must
hear
be
me?
on. Yeah, I can hear you, man. Shweta, you
Sir,
can on the light.
my camera isn't working, sir. So, can I?
No. Third switch. You can put, yeah, third switch. Enough. Fine, man, fine. So let us start the class today without wasting further time. Today, our plan is to revise wave optics and dual nature of matter and radiation because we are going to write a test on those topics in the upcoming week. Today, we are going to revise wave optics and we are going to revise dual nature of matter and radiation. Come first. So let us start with wave optics. So let me give the heading as wave optics. Now, if I talk about wave optics, what is important in wave optics from exam point of view? Let me start talking from exam point of view. From exam point of view, first thing is from this chapter, from the basics, that is Huygens principle. From Huygens principle, expect question to come, and the questions will come generally based upon the definition of wavefront, what are secondary wavelets, what is the shape of wavefront for different conditions. That is the first kind of question that comes in the board examination. About Huygens principle, you will have questions coming in the board exam. Second, in this chapter, is the questions coming from laws of reflection and refraction. So, where they are asking you to prove the laws of reflection and refraction with the help of wave optics, wave principle of light, Huygens theory. So, you have to draw the waves, wave fronts, and make it to get reflected and prove the law of reflection and law of refraction. Both the questions are coming. I'll teach all these things. I just tell you the basics to you know. Third important thing is you may have questions coming from the basics of constructive and destructive interference, where you should understand what is the meaning of coherent waves, why they are important for interference patterns to be visible, when does waves form constructive interference, when does wave form destructive interference, and all those stuff will be there in the third part in this chapter. Next, very important question is certainly going to come from here is YDSE, which is Young's double slit experiment. They'll ask you about the experiment, about the setup, about the derivation, numericals from here, and many theory questions from here. What happens if screen comes close to the slit? What happens if slit are more separated? What happens if you use white light instead of monochromatic light? All these kind of questions are going to be asked in YDSE. And then comes diffraction and very basics of polarization. Generally, nothing is asked from this topic, but still, since it is there in NCERT book, I'm just writing it. Very less of polarization is coming in the board exam, but from YDSE and a bit, very less, only theoretical part. I have taught to you in detail about diffraction. I remember when I taught diffraction, I have spent a good amount of time to make you understand the reason of a bright fringe formation, dark fringe formation. That much deep is not asked in the board exam. They will just ask you very basic theoretical questions from here. So not that detailed diffraction is there. That is all about wave optics. These are the important parts from where the questions are going to come in the board examination. One by one, we will see all these things now. Okay. So this chapter starts with the basic understanding of Huygens principle. And what is Huygens principle? See, Huygens said that lights don't travel like rays as told by Newton in corpuscular theory. He said that light travels as a wave, and wave, it travels in form of wave, and you know how wave behaves. Suppose you have a stone dropped in a place, then you have the formation of ripples. So he said that how the ripples are traveling, the same way the light also is traveling. So he said, if you draw a locus of all the points which are in the same phase, then you get something called as a wavefront. So what is the wavefront? Wavefront is a locus of all the points which are vibrating in same phase. Next comes the secondary wavelets. He also told that all the points on this wavefront act as a source of secondary disturbance. And these secondary disturbance are going to create secondary wavelets. And when you draw the common tangent to all these secondary wavelets in the forward direction, you get a new wavefront. Once again on new wavefront, you will have secondary wavelets. So what is secondary wavelet? If you have a wavefront, on the wavefront, you have the source of secondary disturbance, each source giving rise to secondary wavelet. Draw common tangent, you get a new wavefront. That is the meaning of secondary wavelet. Another thing is shapes of different wavefronts. For example, if they say you like point source, I just now told, then the shape of wavefront will be concentric spheres. If you have a beam of light coming from very far, that is parallel beam of light, then the shape of wavefront will be a plane wavefront like this, isn't it? Shape of wavefront is the light rays passing through a convex mirror, a convex lens, I mean. If you have rays passing through a convex lens, it gets converged, isn't it? They may ask you, what is the shape of wavefront? Before the rays are hitting the lens, it is plane wavefront. After the rays are hitting the lens, it is a spherical wavefront. So remember that wavefronts are always perpendicular to direction of rays. Always remember that wavefronts are perpendicular to what? To direction of incident rays. Direction of rays, which helps you in understanding why are we having different shapes of wavefront. So anything may be asked to you. They may ask you based upon the ray condition. They may ask you to draw the different shapes of wavefront. It's an important question. It comes in the examination. So very frequently, you see last 5 years paper, you can see the questions being asked from here where they are asking you to draw the different shapes of wavefront for different conditions. Then comes the law of reflection and refraction. And if you see the question how it comes generally, they will draw a diagram and give you half diagram. And they will ask you, prove the law of reflection by this. Or sometimes they may not give any diagram to you. Directly they will ask you, prove law of reflection by the wave theory of light. So remember, whenever a derivation is coming to prove reflection or refraction laws, you have to draw a reflecting surface. Once you draw the reflecting surface, step number 1 is to draw the incident rays coming from far, and you will draw the wavefronts like this. And the wavefront which hits the reflecting surface is called as incident wavefront. After drawing incident wavefront, you can mark the point A and B, and then from B, you will draw the next wavefront. For drawing that, you need, tangent, isn't it? So I'll draw a line like this. I'll draw from here arc like this. I'll draw a reflected wavefront, and then it will go like this, like this. So you have incident wavefront and you have reflected wavefront. You will just get two triangles, and both the triangles, you will prove these two triangles are what? Congruent. Don't forget that. The moment you prove that both the triangles are congruent, one triangle, the incident wavefront will have angle of incidence, reflected wavefront will have angle of reflection. So you can prove that angle I is equal to angle R. Please go and see the notes I have given to you. See the previous class video if you want to see. I have done very calmly. Half an hour I have taken to derive this. So I will once again repeat, you will draw the incident rays, you will draw perpendicular wavefronts, and the wavefront which hits the surface is called as incident wavefront. Incident wavefront will have angle of incidence. If I'm drawing once again for you, suppose this is the incident wavefront. If this is the incident wavefront, I'm naming it as AB, then this angle will be called as angle of incidence. And same way, you will draw a tangent, you will draw arc here, you will draw arc here, and you will draw a common tangent to both, and then you will draw the rays like this, going perpendicular. So this was incident wavefront, like this point, let's suppose we C and let this be D. This angle became angle of reflection. So ADC, this CD is the reflected wavefront. And if you take ABC, then AB is the incident wavefront. This angle is angle of reflection. This angle is angle of incidence. So you have to prove angle I is equal to angle R. And then obviously incident ray, reflected ray, and the normal lies in the same plane. So incident wavefront, reflected wavefront, and reflecting surface should also lie in the same plane because they are perpendicular to it. So very important, the question comes from here. If you see if you're going to get the paper next week for this topic, one question will be there, half diagram will be drawn, and then they will ask you to complete the diagram proving the law of reflection by that. Same way, if I talk about the law of refraction, how it is what happens in that? So in refraction, you will draw the incident wavefront, and then when you draw the reflected wavefront like this and like this, they will not have same distance traveled. Why it not have same distance traveled? Because here the medium may have different refractive index, here it may have different refractive index, so the distance traveled by them will be different. And so when you draw a common tangent and when you draw the refracted wavefront, it will be having some bent. So this angle will be called as angle of incidence. This angle will be called as angle of refraction. Here you will take this triangle, and you will just take sine I and divide by sine R, and you will prove they are constant. That is, it will be V1 by V2. This is obviously going to be constant. So this is how you will prove the Snell's law. And once you prove Snell's law, then second law of refraction is done. Obviously, incident ray, refracted ray, and normal lies in the same plane. And since incident wavefront, refracted wavefront, and refracting surface is perpendicular to them, they should also lie in the same plane. So remember, theoretical question, derivation is very important, reflection as well as refraction by using wave theory of light. Note it down, it is very important. I have taught you recently. Check your notes. If you don't have it, check the video of this class and you learn it. This is important topic. Okay, coming to the next topic in this chapter, which is about the basics of constructive and destructive interference. So when I taught you about the principle of superposition, I said you light waves are there. So one wave comes, another wave comes. When they interfere, after interference, there are many possibilities are there. So I said to you, if the first wave is having amplitude A1, second wave is having amplitude A2, then the resultant amplitude will become equal to root of A1 square plus A2 square plus 2 A1 A2 cos pi. This is the equation of resultant amplitude if two waves are interfering and both waves are having different amplitudes. Same way, if you talk in terms of intensity, resultant intensity will become equal to I1 plus I2 plus 2 root I1 root I2 cos phi. If you see both these expressions, you will realize that the net amplitude and net intensities are written here. How it came, I had derived in the class. How I derived? I took vectors. I took if A1 is lying somewhere here and A2 is somewhere here, then the resultant amplitude AR, the angle between them is phi. So I have found value of AR, which is root of A1 square plus A2 square plus 2A1 into cos phi. Also, what is phi here? Never forget that. Phi is phase difference. Very important. Phi is called as phase difference. And how is phase difference linked with path difference? You should remember phi is equal to 2 pi by lambda, which is called as k, propagation constant, times path difference delta x. So phase difference is equal to 2 pi by lambda into delta x, and delta x is called as path difference. So this equation relates phase difference with path difference. Never forget that. Phase difference is the difference between the angles of both the waves, and path difference will become equal to phi into lambda by 2 pi. So from this, if you know the value of phi, you can always find delta x. For simple questions, they may ask you, if the phase difference between two waves is pi by 2, what is the path difference? So you should write this as pi by 2. If you write pi by 2 is equal to 2 pi by lambda into delta x, then pi gets cancelled. This will become delta x is equal to lambda by 4. So if two waves are having a phase difference of pi by 2, they have a path difference of lambda by 4. This kind of questions sometimes is asked for 1 mark in MCQ. So remember, this is the formula which helps you to find phase difference and path difference. Then I taught to you in detail about what is the meaning of constructive interference and destructive interference. So I said, what is the meaning of constructive interference? Constructive interference means where the brightness is maximum. You are having the bright spot. And how the brightness can be maximum? If the amplitude or the intensity is maximum, isn't it? So if amplitude is maximum, you're going to have constructive interference, also called as bright spot. Same way, where you will have destructive interference or dark spot, wherever the amplitude or the intensity is minimum. So wherever the amplitude is maximum, you are going to have constructive interference. Wherever the amplitude is minimum, you are going to have destructive interference. Now, what is, or how will you make amplitude to be maximum? We know the formula of AR, root of A1 square plus A2 square plus 2A1 into cos phi. To make AR maximum, you must have cos phi maximum. Cos phi maximum value is +1. And which value of phi will give +1? The value of phi is 0, 2 pi, 4 pi, 6 pi, and so on. General formula becomes 2n pi, where n starts from where? N starts from 0, 1, 2, 3, 4, and so on. So whenever the phase difference is 2n pi, you are going to get a bright spot. Why? Because if it is 2n pi and you put cos phi as cos 0, it will become +1. Maximum value of cos. Same way, where you will get dark spot, wherever the value of cos phi is minimum. Minimum value is -1. For cos phi to be -1, what are the values of phi? The odd values. Pi, 3 pi, 5 pi, 7 pi, 9 pi, and so on. If I write general formula, then phi will become equal to 2n minus 1 into pi. If n starts from 1, 2, 3, 4, and so on. Not from 0. So I got the formula for phi for bright spot, which is 2n pi. Pi for dark spot, 2n minus 1 into pi. Same way, if I want to find the delta x, where we know that phi is equal to 2 pi by lambda into delta x, which must be equal to 2n pi. Now 2 pi gets cancelled. Delta x becomes equal to n lambda. Now, n lambda means what? If I put the values, I will get delta x is equal to 0, lambda, 2 lambda, 3 lambda, 4 lambda, and so on. N lambda, any lambda is going to give you bright spot. Same way, if I put here 2 pi by lambda into delta x, see, I'm writing the phi formula, phase difference in terms of path difference. It must be equal to 2n minus 1 into pi. Now pi gets cancelled. You get delta x is equal to 2n minus 1 by 2 into lambda. So if you put the value of n as 1, 2, 3, 4 here, you will get delta x is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, and so on. So whenever the phase difference between two waves is 2n pi or n lambda, you are going to get a bright spot, constructive interference. Whenever phase difference between the wave is 2n minus 1 into pi or the path difference between them is 2n minus 1 by 2 into lambda, you are going to get dark spot. That is, if somebody says phase difference between two waves is 36 pi, what kind of fringe is that? Obviously bright fringe, because even pi is bright. If somebody is going to say you are having two waves interfering where the path difference between the wave, phase difference between the wave is 7 pi, it is going to give a dark spot, because 7 pi is odd pi. Odd pi is always going to give dark spot. Same way they say path difference between two waves is 92 lambda. The constructive interference is n lambda. If they're going to say path difference between two waves is 35 by 2 lambda, it is a dark spot, because it is lambda in by 2, isn't it? So we know that all the lambda by 2s are dark spot points. So it's very important to remember the values where you are going to get bright spot and the values where you're going to get a dark spot. It's very, very important. Moreover, if I put the value and check, you are going to get AR as A1 plus A2 or IR as root I1 plus root I2 the whole square. They both are not same. AR being equal to A1 plus A2 or IR being equal to root I1 plus root I2 the whole square, they are not same. That is, if you are having two waves, give me a second. Yeah, sorry. So I was saying that if two waves, they are going to interfere to form a bright spot, the resultant amplitude is the summation of both amplitudes. For example, if one wave is coming, both waves are having amplitudes of 10 units and 10 units. When they are going to interfere to form a bright spot, it will become 20 units, because 10 plus 10 will become 20. But if they are going to have 10 units and 10 units of intensity, root 10 plus root 10 the whole square will become 2 root 10 the whole square, which will become 4 into 10, 40. So intensity becomes quadrupled and amplitude becomes double. Always remember this. I'm repeating what I said now. If you have A1 is equal to A2 is equal to 10. So 10 plus 10 will become 20, resultant amplitude. If you're having I1 is equal to I2 is equal to 10, root 10 plus root 10 the whole square, which is going to give you 2 root 10 the whole square. 2 root 10 the whole square will become 4 into 10, which is how much? 40. 10 became 40 in the case of intensity. 10 became 20 in the case of amplitude. So always remember, in the case of bright fringe formation, in the case of bright spot formation, the amplitude becomes double and intensity becomes quadrupled. Never forget that. Same way, here what will be the value of amplitude? AR will become A1 minus A2. And what will be IR? IR will become root I1 minus root I2 the whole square. Which means if you have 10 and 10, same values, AR will become 10 minus 10. How much is that? 0. Here root 10 minus root 10, 0. So when you are getting a destructive interference, there will be no amplitude there. Obviously, darkness will have no amplitude. And where you are having dark spot, there will be no intensity. And where you are having bright spot, it will be 4 times. I hope you're getting my point. Okay. So if the amplitudes are same, then resultant amplitude is always double the value of initial, and intensity is quadrupled, whereas in destructive interference, it is 0 for both the cases. This is the base to understand YDSC and to understand diffraction. Without knowing this, you cannot think about YDSC understanding. Because what is the meaning of YDSC? YDSC experiment was done by Young. And what did he do? He took like this slit. And in front of slit, he kept screen. There are 2 slits, S1 and S2. And then on the screen, he observed what are the interference pattern. He saw the interference pattern on the screen was something like this, where he was getting a bright spot here. Like if I talk about center was a bright spot. Then you have a dark spot. Once again, you have a bright spot. Then you have a dark spot. You have a bright spot. You have a dark spot, and so on. Bright, dark, bright, dark, bright, dark. Down also bright, dark, bright, dark, bright, dark. This was what the observation of Young. So when he saw on the screen, center was a bright spot, and then you had a dark spot, then you had a bright spot, then you had dark spot, and so on. Same way here, bright spot, dark spot, bright spot, dark spot, like that. This was the interference pattern visible on the screen when light was passed through here. So here there was a light source taken and light was made to pass through a convex lens to make a strong beam of light. And when we saw it, it happened. Why it would have happened? Because Young told that light would have entered like a wave like this. And when these waves are interfering, based upon the interference points, it is decided whether it is going to be a bright spot or dark spot. So who is the deciding factor? Deciding factor is how the waves are interfering. Waves interfering at n lambda is going to give you bright spot. Waves interfering at 2n minus 1 by 2 into lambda is going to give you dark spot. So from there, with derivation is very important for here. I'm not going to do derivation now. You just check the notes if you want to do the derivation. We got the formula of y of nth bright spot as n lambda d by d. I have taught you in detail how it has come. And y of nth dark is 2n minus 1 by 2 into lambda d by d. So this makes it clear how or what is the location of nth bright fringe, nth dark fringe. Always remember, lambda is wavelength of light, capital D is distance between the slit and the screen, small d is distance between the slits. If they ask about angular position, theta of nth bright, that will become equal to n lambda by d. Capital D will not be there. Or angular position of nth dark spot, it will be 2n minus 1 by 2 into lambda by small d. These are the angular positions for nth bright spot and nth dark spot. I hope it is clear to you. That is about identifying and finding location of dark spot and bright spot. If I ask you what is the fringe width, beta they call it. Fringe width is, what is the formula? Lambda d by d. So lambda d by d is the formula of fringe width. If it is angular fringe width, then it will be lambda by d. So the fringe width is the width of each fringe, whether it is bright fringe or dark fringe, bright fringe or dark fringe. Every fringe will have the same width. One thing I want to make you understand here, these derivations, whatever we did in the class, are based upon some assumptions. What are the assumptions? First assumption was lambda is much less than small d is much less than capital D. That is, wavelength of light is much smaller compared to distance between the slits, and distance between the slit is much smaller than distance between slit and the screen. So remember that lambda, small d and capital D, everything should be linked in the same way as I told. Like you should not have difference in this, because if you have difference in that, you will not be able to get this values itself. I hope you understand my point. So if you don't have this relationship, then these formulas are itself invalid. Okay. Next, I told you the amplitudes must be same, nearly same at least. That is, the amplitudes of both the waves. I'm saying the answer for a question now. Remember that. The question is, what are the conditions for distinct interference pattern? The answer is, the first answer is this. Second is, amplitudes of the waves must be nearly same, because only if they are same, we are going to get perfect dark spot. The perfect dark spot means if A1 and A2 are 10 and 10, then it will become 0. If it is 10 and 5, 10 minus 5 will remain 5. So we will have some brightness there. I hope you get my point. At the dark spots, we want 0 amplitude. If some amplitude goes there, then in dark place also we'll have some little brightness, which will disturb my interference pattern. Where it is bright, I want the maximum brightness. Where it is dark, I want complete darkness. Otherwise, you may have some errors, because at dark spot, you will get some brightness. Coming back, another assumption is there. That assumption is light must be monochromatic. That is, we should not use white light. If you are going to use white light for YDSC, then you are not going to get distinct interference pattern. Why? Because white light is a mixture of 7 different colors, and 7 different colors have 7 different wavelengths, and 7 different wavelengths will have 7 different positions. So one bright spot, if n lambda d by d, lambda of blue is different, green is different, red is different. So all the different colors will have different locations of their bright spots and dark spots. You are going to have a blurred interference pattern. So if you use monochromatic light, only then you can get the perfect distinct interference pattern. You should never use white light. Remember these points. It's very important. Otherwise, you will not be able to see interference pattern itself. One last point is the sources must be coherent. Because if you have coherent sources, then the interference patterns will be time independent. This also I have taught to you how. If they are non-coherent waves, then the phase difference starts depending upon time. And if it starts depending upon time, as time is changing, phase will change, phase is changing, amplitude will change. So where you are having bright spot, it will become dark, and dark will become bright. So So you're going to have once again a blurred vision, dark, bright, bright, dark, dark, bright, bright, dark. You're not able to see some pattern. So only if these four criteria are fulfilled, waves are coherent, lambda is much, much less than small d is much, much less than capital D, A1 is almost equal to A2, and light is monochromatic. Then only you will be able to see distinct interference patterns. Okay, this is all about the YDSC. Now coming to diffraction. What is diffraction? So diffraction is a phenomena by which the light bends. It bends where? It bends at sharp edges or corners or thin openings. So remember that if you have very, very small opening, or you have sharp edges, or you have sharp corners, that place the light tends to bend. That bending is called as diffraction. For example, if I'm having a pinhole like this, a small hole in this thing, and behind if I'm having a screen and I pass light through this, then I can see some fringes forming here. Or if I'm having one single slit, but very thin slit, and I'm having a screen behind it, then I'm going to see some fringes pattern here. This is called as diffraction. Diffraction means light is bending and going there. So bending of light when it is passing through small openings, passing through sharp edges or sharp corners, that phenomena is called as diffraction. So diffraction happens. For understanding diffraction, you must understand single slit diffraction. Now, what is single slit diffraction? Before I talk about single slit diffraction, I want to make one thing very clear to you. Remember that interference in YDSC are happening because of the interference between the wavefronts. I said before some time that when the experiment was conducted and we are able to see this kind of fringes forming here, the reason of fringes forming is the interference between what? Between the wavefronts. Waves are having wavefront, wavefront interfering. After they're interfering, wherever they interfere with part difference of n lambda, bright spot. Part difference of 2n minus 1 by 2 into lambda, dark spot. In the case of diffraction, it is the interference between wavefronts. Sorry, wavelets, not wavefronts. That's why a single light itself can give you diffraction. See, patterns you can see only if two things are intersecting. If two things are intersecting, only you can get the diffraction, any patterns. If you're getting patterns, means something has intersected. But single source, how it can intersect with itself? So we understood that it's not single source. I said in the beginning of today's class, a single source behaves like a source of many, many small secondary disturbance. These secondary disturbance will produce secondary wavelets, am I right? And these secondary wavelets will draw common tangent, new wavefront. So what did Young say? He said that these secondary wavelets are interfering, right? The interference between the secondary wavelets is giving rise to diffraction pattern. And it was wavefront interference that gives rise to interference pattern. So if you see the pattern, if I'm drawing the pattern here on the screen, it was observed that the pattern on the center was a central bright, and then you have dark, then you have first bright spot, once again dark, then you have once again bright spot, and then you have dark spot. That's how it is there. Once again dark spot, then bright spot, then dark spot, then bright spot, then dark spot, and then bright spot. This was the observation. Very clearly visible to you on your screen that the central bright is bigger, other bright are smaller. First of all, how the center is brighter, that we will understand. Next, we'll understand how the brightness is going in the other place also. So how did they explain? Please pay attention, guys. So I'm having the slit and having the screen at the center. If suppose I'm having many, many sources, I'm dividing in 100 sources. The first source and last source are interfering with each other. Path difference, 0 between them. Because same path, you see, A, P, if you have B, P, they are having same path length. So they are having 0 path difference. For delta x 0, we are having bright spot. Same way, the second and the second last, third and third last, fourth and the fourth last. All these waves are having 0 path difference, and since 0 path difference gives central bright spot, I am going to get the central point as bright spot because all the waves are having a path difference of 0. One more way of understanding is the layman's way. What is that? Imagine that this source is divided in two equal parts. Okay, this part and this part, both halves are going to interfere, and then they are going to form a bright spot because there is no path difference between them. Layman's way of understanding. A practical way of understanding is, on one wave front, we have millions of sources of secondary disturbance. First and the last source, second and second last source, third and third last source. Like that, every source which are having a path difference of 0, they will interfere and form central bright. That is, at delta x equal to 0, we are going to get central bright. Okay, where will you get the first bright in the case of diffraction? Where are you going to get first dark? First, tell me that. So what is the location of nth dark, y of nth dark? Any idea? It is n lambda d by a. Basically, in diffraction, we have capital D as distance between slit and screen, and small a as open slit width, we call it slit width. If you see here, you will realize that this was the formula of bright spot in the case of interference by DSC. But in diffraction, n lambda d by a becomes for dark spot, bright spot, sorry, dark spot. In the case of YDSC, I'll go to the previous page, you will see. In the case of YDSC, what did we have? Nth bright, we had n lambda d by d. In the case of diffraction, for dark, you have n lambda d by a. Moreover, for y of nth bright fringe, what do you have? 2n plus 1 by 2 into lambda d by a. Now, how all these things happen? I explained to you very well in the class when I taught it to you. I will just give a quick recap about whatever I told you. I said that in the case of, so you are understanding that all the dark spots are forming at delta x is equal to lambda, 2 lambda, 3 lambda, 4 lambda, and all the n lambda, except n is equal to 0. So delta x is equal to n lambda, where n starts from 1, 2, 3, 4, and so on. I am going to get dark spot, which is contradicting with my theory, because my theory says that n lambda is a point of bright spot, but here I'm getting dark spot. What is the reason for that? Reason was found that if I see the location of first dark I'm finding, this is the path. Even if they have some path difference, let this be A, let this be B, let this be P. So AP is the path from the top, BP is the path on the bottom, BP is longer than AP. So this is called as the path difference, delta x. So path difference is there. How much path difference is there? That is BP minus AP. Remember that. So this path difference, when it is lambda, I am getting dark spot, which means what? The first and the last are having a path difference of lambda. See, if you don't want to confuse yourself more, once again, I'm repeating, divide into two parts. If divide in two parts, the first and the last half will cancel each other. And so we have no brightness available there. But if you want to understand technically what happens inside, I can say like this. If 1 and 100 is having a path difference of lambda, 1 and 51 will have path difference of lambda by 2. Half I am taking. 2 and 52 will have path difference of lambda by 2. 50 and 100 will have path difference of lambda by 2. It means all the waves in this source which are having a path difference of lambda by 2, which is obviously dark spot point, only are interfering. So I am getting a dark spot there. How do I justify the bright spot at this point? That is, if you see delta x is equal to 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, 9 lambda by 2, and so on. It means the general formula becomes 2n plus 1 by 2 into lambda, where n starts from 1, 2, 3, 4, and so on. So how this is giving dark spot, bright spot, we will understand that. Same logic. If I'm identifying the first bright, the first and the last source is giving bright, isn't it? That is 1 and 100 is having path difference of 3 lambda by 2, as I say. The first bright at 3 lambda by 2. If first and the last is giving 3 lambda by 2, 1 and 34 will give lambda by 2. 1/3 I'm dividing. And 2 and 35 is going to give lambda by 2. Like that, 33 and 66 is going to have lambda by 2. 67 and 100 will have lambda by 2, but 68 will not have. 69 will not have. All they will not have any pair itself. So remaining 33% of the waves are not going to interfere. They are going to form the bright spot. The central bright was formed by 100% of waves, but first bright was formed by only 33% of waves. That's why the brightness also is less. So central bright will be very bright. First bright will be less bright. How much less? 33% of the central bright. Same way, second bright forms at 5 lambda by 2. It means what? 1 and 100 is having 5 lambda by 2. So 1 and 21 will have lambda by 2. Like that, if you find all the 2 and 22, 20 and 40, 40 and 60, everything, but 81, 82, 83, they won't have any pair. It means 20% of the waves are not having their counterparts to interfere and become dark. They will form brightness. So central bright, 100% of the waves are involved in brightness. First bright, 33% waves are only involved. Second bright, 20% only involved. So as we are going away from central bright, my brightness is reducing. That's why when I draw a graph between intensity and the phase, that is, this is at 0, then we have actually lambda by 2, nothing is there, but then also I'm writing. Then we have lambda. Then we have 3 lambda by 2. Then we have 2 lambda. Then we have 5 lambda by 2. 3 lambda, and so on. I'm drawing all the points. So 0 is for central bright. Let the intensity be this much. Okay. Lambda is a point of dark spot. Then 3 lambda by 2, bright spot. But how much bright? 33% bright. Isn't it? Then 2 lambda, dark spot. 5 lambda by 2, 20% bright. 3 lambda, dark spot. Once again, 20% bright and dark spot. If I draw the graph is like this. Are you feeling that? The intensities keep on reducing as I'm going away. First bright, 100% of the waves form the brightness. Here, 33% of waves are forming. Here, 20% waves are forming. So as you go away from central bright, the wave brightness keeps on reducing, the fringe brightness, and it will fade off ultimately. So interference in YDSC will never fade out. It will remain same from top to bottom. But in diffraction, central will be very bright, and as you go away, brightness keeps on reducing, becoming negligible, almost 0 in the very far end. That's how the diffraction works. Interference works like this. It is having equal values like this. Like this. One more thing I want to say here. If you see here, the width is bigger for central bright, but other brights are having small width only. Are you feeling that? So if I write what is the fringe width, which is beta of central bright, answer is 2 lambda d by A. But general fringe width formula is lambda d by A. Only central bright is bigger. Same way, angular theta of central bright will become equal to 2 lambda by A, and theta of other brights will become equal to lambda by A. That is how we are determining what is the fringe width of central bright and what is the fringe width of other brights. Clearly indicating it is double. Other things are lambda d by A. And again, I am writing the location. Y of nth dark will be n lambda d by A, or theta of nth dark is n lambda by A. Same way, y of nth bright is 2n plus 1 by 2 into lambda d by A, or if I am writing theta of nth bright, it is 2n plus 1 by 2 into lambda by A. Remember, these things are very, very important. Expect numerical to come from here itself. So, if you don't remember the formula, or if you make a minor mistake in the formula, everything will become wrong. It's very delicate because it's sometimes confusing. For YDSE, brightness is n lambda d by d. For diffraction, brightness is 2n plus 1 by 2 into lambda d by A. In the case of interference, YDSE, darkness is 2n minus 1 by 2 into lambda d by d. Here, darkness is n lambda d by A. N, how it starts? In these two things, n starts from 1, 2, 3, 4, and so for both. So if you don't remember these things, fair chance you will make a mistake. Because diffraction, generally questions are coming from graph only. Remember that. Theoretical questions will come, graph questions will come. Numericals comes only from YDSE. In the board examination, don't expect numericals to come from diffraction. They don't ask. School exam they may ask also, but in the board examination it is not in portion. Numericals based upon diffraction is not there. You have numericals based only upon YDSE. Only theoretical part of diffraction is there, and there expect them to ask questions from graph or theoretical values or reason for diffraction patterns to be visible. So reason for diffraction is interference between the secondary wavelet. Reason for YDSE was interference between the wavefronts. So they may ask a question like, how is interference different from diffraction? You must be writing, in interference, all the fringes have same width. In diffraction, central bright is bigger and other fringes are having same width. In interference, you should write, YDSE you should write, all the fringes are having same brightness. In diffraction, you should write, central is more brighter and the brightness fades away as you go away from central bright. For YDSE, you can write, it is formed by the interference of wavefronts. For diffraction, you can write, it is formed by the interference of secondary wavelets. These kind of questions are often asked for 2 mark or 3 mark. Difference between YDSE and diffraction. I hope it is clear to you. Next in this chapter is a very small topic, least important, but theoretical question may come, which is about the polarization. Polarization. So what is polarization? Polarization means you are cutting some intensity of brightness. It means whenever the light is electromagnetic wave and it may be going like this. When I'm drawing this, it means I'm drawing in 2 directions, into the plane and up and down. If it is made to pass through a polarizer, now based upon how the polarizer is, if I'm having a slit like this, then only this will pass through it. Isn't it? So what did we do? We reduce the intensity of the light. Why this not passed? Because I have no permission for it to pass. So I'm stopping some of the waves. So if you are restricting the intensity of the light when it is passing from one place to another place, this phenomena is called as polarization. So what we do by polarization? We reduce the intensity of light. That's why polarizers are used in spectacles, coolers, where we are wearing in this hot summer day, right? Coolers. Why we are wearing? Because they are cutting some of the sunlight. How do they cut the sunlight? By using polarizers inside. So polarizers will not make all the light to come inside. Some light it will restrict. If you keep another thing, that is called as analyzer. Again, your wish, you can keep like this also, you can keep like this also, completely your wish. If you keep like how I kept initially, then nothing will come out, isn't it? Nothing will come out. But if I keep something like this, then once again the same thing will come out. Are you getting my point? So the angle between the polarizer and the analyzer, it decides what will be the intensity of the final radiation. That is, the formula is I is equal to I naught into cos square phi by 2, if I am right. This is what the book is giving, right? NCERT book's formula is there, I think. I is equal to I naught cos square phi by 2. Is it there? See the thing, it will be mentioned there. Down you see there, Shweta, yeah. I is equal to I naught cos square phi by 2. Am I right? Not by 2 it's given. Okay. Malu's law, it is. I is equal to I naught cos square theta. Now this decides whether theta, what is theta? Theta is the angle between polarizer and analyzer. If you see like this now, they are having 0 degree angle between them. So if cos 0 is 1, I will be same as I naught. But suppose I kept like this, analyzer I kept like this. Now angle between this and this is 90 degree. What is cos 90? 0. So I will become 0. So final radiation will have how much intensity? It is completely a function of what is the angle between polarizer and analyzer. If they're parallel, same intensity will come out. If it is perpendicular, no intensity will come out. If it is at some angle 30 degree or 45 degree, based upon the angle, some intensity will come out. That is all about polarization. That is all about wave optics chapter. So I told you in the beginning itself, in this chapter, what things you have? In this chapter, you have Huygens principle, from where the questions will come, like definition of wave fronts, secondary wavelets, how the wave propagates. They may ask you shapes of wavefront for a point source, for an infinite source, for passing through a prism, passing through a lens. That kind of questions will come. Draw the shape of wavefront. Second, I told laws of reflection and refraction. They may give you half diagram and they may ask you to complete a diagram, or they may ask you entirely derive and define the law of reflection and refraction by using wave theory of light. There, you must remember that in reflection, we are proving two triangles as congruent, and then we are proving angle I is equal to angle R. In the case of refraction, we are taking two triangles, we are finding sin I, sin R, and then proving V1 by V2 is a constant, Snell's law. Then comes basics of constructive and destructive interference, where you should understand that wherever the constructive interference is taking place, the phase difference is n lambda, path difference is, that is path difference is n lambda, phase difference is 2n pi. And destructive interference takes place as 2n minus 1 by 2 into lambda as a path difference, and 2n minus 1 into pi as a phase difference. From there, the question may come, numericals may come, some theory questions may also come there. Resultant amplitude is A1 plus A2 in the case of constructive interference, A1 minus A2 in the case of destructive interference. Then we talked about YDSZ. From here, numericals will definitely come in the school exam and board examination. Numericals will come like, they will ask you to find the location of nth bright, nth dark, fringe width can be asked, or lambda can be asked, any kind of question can be asked. The formula remains the same. Y of nth bright is n lambda d by d. Y of nth dark is 2n minus 1 by 2 into lambda d by d. Beta, that is fringe width, is equal to lambda d by d. In the case of diffraction, the location of nth dark, which is not going to come in the exam, but it's just for knowledge I'm telling you. Nth dark is n lambda d by a. Nth bright is 2n plus 1 by 2 into lambda d by a. And fringe width, central bright is double, 2 lambda d by a. Other fringes are having lambda d by a. Remember that in diffraction, the waves are going to fade out. The intensity is going to reduce. In YDSC, it's going to have same brightness throughout the screen. Polarization is a principle by which we are cutting off some intensity of the radiation by keeping polarizers and analyzers. One formula is there, I is equal to I naught cos square phi, cos square theta, where theta is the angle between the polarizer and analyzer, which decides how much ray will be the finally coming out from the polarization principle. So all these things are there in wave optics chapter. I think if you whatever I told you, if you understood that and if you're going to study that, then you will not lose any marks in this chapter. Nothing big is there in this small chapter. It is simple chapter. Then comes dual nature of matter and radiation. Let us talk about that. What is important from that chapter point of view? If you see, if I go to the next chapter, that is dual nature of matter and radiation. It's more smaller chapter, but once again, expect at least 6-mark questions to come from here. 5 to 6-mark question is coming. So it's a scoring chapter. Small, simple chapter, 6 marks giving to you. What do you want? You know one thing? Even electric field and charges. Big chapter, 6 mark only. Even potential and capacitance, 7 marks. Big chapter, huge chapter. But this small chapter is going to give you same 6 mark. So it's actually scoring things for you. You should not miss mark in this chapter for sure. Okay. Dual nature starts with the basic understanding of work function. Now, what is work function? Work function is given by phi naught. What is that? Work function is the minimum amount of energy required to eject the electrons from a metallic surface. So, if you have a surface, metallic surface, and you want the electron to get ejected, how much energy is required for that? Minimum energy required for ejecting ejecting an electron from the metallic surface is called as work function. Different metals will have different work functions. The formula of work function is what? Phi naught is equal to h nu naught, where h is called as Planck's constant, nu naught is called as threshold frequency. Minimum frequency required for ejecting electron is called as threshold frequency. And remember that phi for different is different. Like for example, cesium is having least, which is I think 2.16. I don't remember the value exactly, something like that only. And platinum has maximum. How much is that? 5.65 electron volt, approximately. Like sodium, potassium, calcium, every metal will have different work function. It means different metals, by their structure, we need different amount of energy for ejecting the electron from their surface. Remember that. That phenomena is called as work function, by which you are removing the electron from the metallic surface. Now, how are the electrons are ejected? That is, you must know what are the methods of electron ejection. Methods of electron ejection. There are 4 methods. What are those? The first one is called as thermal emission. The second one is called as electric field emission. The third one is called as secondary emission. And the fourth one is called as photoelectric emission. Very important for this chapter. So what is thermal emission? When you supply heat energy, and by that heat energy, the electron gets emitted. That is called as thermal emission. And the electrons that are going to come out are called as thermions. What are thermions? Thermions are the electrons which are ejected when heat energy is given to a metal surface. So if electrons are getting ejected by heat energy, that emission is called as thermal emission, and the electrons which are ejected by such method is called as thermions. Electric field emission is keep a metal surface in some strong electric field. If you keep in strong electric field, electron will be repelled by negative plate, it will be attracted by positive plate, the electrons will come out of the metallic surface. So if electrons are being ejected by using some high electric field, that is called as electric field emission. Secondary emission means by beating or by rubbing or by hammering a plate, if you are able to eject the electron, that is called as secondary emission. And the last one and the most important one is called as photoelectric emission, where light of suitable intensity is made to hit on a metallic surface, electrons get ejected. That phenomenon is called as photoelectric emission. Photo means light. So he told that light is having some energy, and energy of the light is given by h nu. Nu is frequency of radiation. When you multiply frequency with Planck's constant, you get the energy of incident radiation. And that energy is only supplied to the metallic surface. And if the energy is sufficient, that is more than the work function, then the electron will get ejected, and this phenomena will be called as photoelectric emission, by which photo means light. Light is used for ejection of electrons. Then comes the photoelectric emission concepts, where the first topic is Halbeck and Lenard's experiment. And believe me, the whole chapter is depending upon this experiment only. That is, you are going to get the question from only from here. I mean, you may get from this also, that is wavelength of electron also, de Broglie's wavelength. But then also, mostly the question comes from Halbach and Lienard experiment only. What type of question is coming? For that, you should understand what is the experiment all about. In this experiment, the Halbach and Lienard took a cathode ray tube like this. In this tube, they kept two metals, two plates. One is called as collector plate. Another is called as emitter plate. This one is emitter plate. And this one is called as collector plate. And then here you have a galvanometer to check any current is coming or not. When you have some light hitting the metal plate and light is having sufficient energy, more than the work function, then electron may come and may jump and go to this plate. And if the electron is moving through it, current is produced, galvanometer will show some deflection. Very less, microampere. But that current comes. That current is called as photoelectric current. So this is the experiment in which there was a cathode ray tube taken. Cathode ray tube had two plates. One is emitter plate, which is ejecting electrons by supplying energy on the metal plate. Second is called as collector plate, which is collecting the electron, and it's connected with a galvanometer, which will show whether current came or not. There is a secondary connection by which we can control how much is the, we can increase the photoelectric current, we can decrease the photoelectric current. For controlling that, we have a secondary connection. NCERT book, very good diagram is given for a secondary connection, which I have also told in the regular class. There are 4 graphs here. All the 4 graphs are very, very important for the board examination. The first graph is the graph drawn between intensity of the incident radiation and photoelectric current, and the graph came like this straight line, which demonstrates that, which tells that increasing the intensity of photoelectric, that is incident radiation, is increasing the number of photoelectrons emitted per second. See, when the photoelectric current is increasing, how it can increase? If more photoelectrons is getting emitted per second. So what did he conclude? He concluded that with increase in intensity of incident radiation, the photoelectrons emitted per second is increasing. And that is why the photoelectric current is increasing. This is the first graph, very important for the examination, where the graph is between photoelectric current and intensity, clearly indicating that intensity increasing is increasing the photoelectric current. I can even draw opposite, like I can draw the intensity in this side and I can draw the photoelectric current on this side. Again, it is linear only. So as you increase the intensity, the photoelectric current keeps on increasing. Then comes the second graph. Second graph again is a graph drawn between the photoelectric current and the voltage potential. First case for a fixed frequency and varying intensity. So I'm having the graph between photoelectric current and potential. I'm taking 3 different radiations, and all 3 are having different values of intensity, where I1 is maximum, I2 is less than that, I3 is minimum, which I'm writing here. I1 is more than I2 is more than I3. It means I'm having, see, in this chapter, we will have 2 important terms, intensity and frequency. When I say intensity, it means brightness, more bright, less bright, like that. When I say frequency, means color changing. That is, frequency determines the color, intensity determines the brightness. So if you see here, intensity I1 is maximum, and as per the previous graph, we can understand that more intensity means more photoelectric current. That is why we have higher current for I1, because I1 has maximum intensity. I3 has minimum intensity, it has minimum current. Now what we do, we give positive potential. What is the meaning of positive potential? See, if we make our emitter plate negative and collector plate positive, what is going to happen? I am going to support my photoelectric current. That is, whatever electron is getting ejected, if this plate becomes negatively charged, it will repel it, and this plate becomes positively charged, it will attract it. So I am supporting photoelectric current. If you are supporting photoelectric current, then you will see an increase in the value of current. And that's what happens, increase and get saturated. Once again, increases, get saturated, increases, get saturated. So we understood that as we increase the potential, that is, as we give the positive potential. Why I'm saying positive potential? Because I'm supporting the photoelectric effect. I'm making the emitter plate negative, collector plate positive. So my photoelectric effect becomes more easy, and the photoelectric current increases. What I do next? I give negative potential. Negative potential means I'm making this positive is becoming negative. What will happen? I'm opposing photoelectric current now. If imagine this plate becoming negative and this plate becoming positive. Now electron is coming out, it is pushing, it is attracting. So I am opposing photoelectric effect. I want the current to become less. Same thing happens. As we proceed, we are going to see that it is reducing, becoming zero at one point. Surprising thing was, all the three intensities has same stopping potential. Stopping potential for the first intensity, second intensity, and third intensity all are same, which was quite surprising, because different intensity of radiations have different number of photoelectrons emitted, but stopping potential for each intensity is same, even though the values of intensity are different. How Einstein concluded this? He said that intensity of the incident radiation affects only the number of photoelectrons emitted per second, but the energy possessed by the photoelectrons remains same. Or I should say that maximum kinetic energy by the electron remains same. It means that in case if I1 is releasing 100 electrons, I2 releasing 500 electrons, I3 releasing 1000 electrons. Ulta I am writing actually. I1 is maximum. 1000 electrons, 500 electrons, 100 electrons. But these 100 electrons are having energy between 0 to 10 joules. This is also having from 0 to 10 joules only, and this is also having from 0 to 10 joules only. Now, if you ask me why I'm giving a range of energies, because all the electrons will not have the same energy. Why do I say so? Imagine this is the metal surface. Electrons are not in the same position, right? Some electrons are inside, some are outside, some are like more above. When I'm giving energy to it, this electron will come out easily. This will take some energy to come. This will take more energy to come. So this electron will be fastest when it's coming out. It has more energy remaining. This will be slowest. So when electrons are getting emitted from the metallic surface, don't think that all the electrons have same energy. The electrons present in the upper layer of the metals will have higher energy. Electrons present in the lower, like inside the metal surface, will have lesser energy. That's why if it is coming out, one electron will have 10 joule energy, one may have 1 joule energy also, one may have 5 joule energy also. So how much energy is there in the electron is completely a function of from where it is coming out. Topmost surface, maximum energy. Bottommost surface, least energy. So I'm talking only about the maximum kinetic energy. So if you see in these three cases, 10 joule, 10 joule, 10 joule, it means that intensity does not affect the energy of the photoelectrons. It affects only the number of photoelectrons. More electrons, but maximum energy is. So in this case, you will not have any change in the stopping potential, because what is the meaning of stopping potential? Stopping potential means energy given to stop the photoelectric effect. So here how much energy is required to be given to stop? 10 joule. For this, 10 joule. For this, 10 joule. So how much energy you give to stop it remains same. And what is that? EV naught is the energy. Formula of energy is EV naught. From here we get the concept like EV naught must become equal to half mv max square. This is the formula which relates potential energy. EV naught is potential energy and half mv max square is the kinetic energy. Second graph is drawn between the same potential as well as frequency, varying frequency, but same intensity. So once again, we came to know that suppose this is new 1, this is new 2, this is new 3, and obviously nu1 is more than nu2 is more than nu3. When we gave the increase in potential, it got saturated. It also got saturated. It also got saturated. Surprising thing was they are getting saturated in the same point. But stopping potential was different for different metals. So it has different stopping potential, it has different, and it has different. This graph justifies that if we are using different frequencies of incident radiation, the frequencies are only affecting the energy, but intensity is same for all three. It means number of photoelectrons is same. If in the first case it is 100, second case 100, third case also 100. But in first case, the energy may be, maximum energy may be 20 joule. In second case, 10 joule. In third case, only 5 joule. So the energy required to stop in third case also is the least. And first case is the most. So how much energy you are spending to stop the photoelectric effect is also less if the energy present in the electrons is also less. So electrons coming out, some electrons coming out with 20 joule energy. In second case, 10 joule energy. In third case, only 5 joule energy. The energy required to stop it also is less for the third case. That's why it has a different stopping potential. So these experiments confirm that frequency of incident radiation is a function of maximum kinetic energy possessed by the electrons, and intensity of incident radiation is the function of number of photoelectrons emitted per second. It's a very important theoretical part. Expect questions to come for sure from this concept. So it is impossible that no question comes from here. Question is definitely going to come from here. Then comes the fourth graph. Fourth graph, if you see, the fourth graph is drawn between the frequency and the stopping potential. There is a frequency here and there is stopping potential here. So if you see, the graph is like this. They have drawn two different metals, metal A and metal B. NCERT book is having all these graphs. So the first graph says that there is a minimum frequency required to start the photoelectric effect. That is called as threshold frequency for this metal A. And different metals have different threshold frequency. That is only showed by this graph. You see the first graph, A, it has less threshold frequency. Metal B has more threshold frequency. It means the different metals will need different energy to start photoelectric effect. And second thing, as we are seeing, as the frequency is increasing, stopping potential is also increasing to stop it. Obviously, because more frequency means more energy. You know that energy is equal to h nu. If you're giving more frequency, energy is more. If energy is more, energy required to stop also is more. That's what this graph says. This graph says that every metal has a threshold frequency. Before this threshold frequency, photoelectric effect will not start. And second thing, as you increase the frequency, stopping potential also increases, which indicates that frequency increasing is increasing the maximum kinetic energy possessed by the electrons. So the energy required to stop it is also more. After this, we have Einstein's photoelectric equation, for which he got the Nobel Prize. What is the equation? Very simple equation. He said that whatever energy the light is coming, h nu, is used for two things. One thing, to eject the electrons out from the metallic surface, plus the kinetic energy it is going to possess. So this is the Einstein's photoelectric equation. Many ways you can write it. I can write nu as c by lambda, cc gets cancelled, h into 1 by lambda minus 1 by lambda naught, everything. Instead of half mv max square, I can write ev naught also. So there are many ways you can write the equation. But don't confuse yourself. Remember, the equation is h nu is equal to h nu naught plus half mv max square, where h nu is the energy supplied. Energy supplied by what? By the light. H nu naught is work function actually. It is work function. So instead of h nu naught, I can also write phi naught. Somebody is writing h nu is equal to phi naught plus ev naught. They're also right. This is also same equation only. Because half mv max square is always equal to ev naught. And this is the maximum kinetic energy possessed by the electrons. So based upon this, quite a couple number of times we have numericals from this chapter. If numericals are going to come, you may expect numericals to come from this equation only, where you have to put and find the value of kinetic energy or velocity or potential, solving potential, anything may come. That is about Einstein's photoelectric equation. And then in this chapter, we have wave nature of matter. So we talked about wave nature of radiation. Now we have wave nature of matter, which was explained by whom? It was explained by de Broglie, who gave de Broglie's wavelength. What was de Broglie's wavelength? He said that lambda is equal to h by mv, isn't it? Lambda is equal to h by mv is the de Broglie's wavelength of the matter. He said that every matter which is moving has a wave linked with it, and the position and the momentum of the particle in this wave is uncertain, which was given by Heisenberg's uncertainty principle, not required for the physics. But what is required for physics is this wavelength equation. Matter waves wavelength lambda is equal to h by mv, very clearly indicating that more the velocity, less the wavelength, you can feel the wavelength. Lesser the velocity, bigger the wavelength, you cannot feel it. That is, if wavelength is like one crest is here, one crest is in America, I cannot feel the wave nature. But if one crest is here, second is here, third is here, fourth is here, I can feel the wave nature. So when you can have shorter wavelength, when we have higher velocity. So objects moving at very fast velocities, their wave natures can be felt. But objects moving at lesser velocity, we cannot feel the wave nature. But that does not mean it is not existing. It is existing still. De Broglie also gave the de Broglie's wavelength of an electron, which is given by the formula. What is the formula? 13.36 by root V naught, something like this. Check whether it is correct or some 12.27, I think it is. Sorry, 12.27, isn't it? Check it. If you're having any notes or any book, what is de Broglie's wavelength for electron? I think it is 12.27 by root V naught Armstrong. This is the lambda for moving electron. And from here also some questions can be asked. If V naught is given to you, you can put in this and get the answer. If you want me to tell the equation, then the lambda E value is h by root of actually 2m E V naught, like this. Or you can also write h by 2m into kinetic energy max. This also you can write root of. So lambda of electron can be written as this or can be written as this. From here also numericals can be expected, or some questions, reasoning questions can be expected. So remember, these kind of questions can be asked from dual nature of matter and radiation. Both chapters, wave optics and dual nature, are simple theoretical chapters. So practice well, and I think it is simple chapters. Nothing much is there in these chapters. Okay, so I'm winding off here. We'll meet again in the next class. Please write a test properly. Don't miss the test for any reason. Okay. Bye-bye. Take care. We'll meet again in the next class.
Thank you, sir.
Yeah.